we'll get started and continue on here. Okay. Okay, so let's just talk about describing data. Okay, so our data, we gather data and we've got a bunch of information. Alright, so just imagine we've got a table of data, and so let's say we went around this classroom and we listed off, we just asked each student, you know, what is your gender, your height, your age, your hair color, things like that. Okay, so we say, so we get your name, and then we have gender, height, age, hair color, etc., etc., etc. Okay. All right, and it doesn't matter, but let's say, okay, so we have, you know, Mary, female, 5'2", age 24, hair color brown. Joe, male, 5'9", 26, black hair, etc., etc. Okay, so we got. We can imagine gathering a data set like this. Okay. Each line, each different person, or each subject, or each line in this table is an individual, and we call these cases or subjects. Okay. Case or subject. Okay. And the columns are variables. Okay. So the columns are variables, and we have two types of variables. We've got categorical variables, and we have numeric variables. Okay. Sometimes numeric variables are called quantitative variables. Sometimes we'll say qualitative or categorical. But that's whatever. Okay. Categorical variables and numeric variables. Categorical variables, they tell us what type or what kind. Numeric variables, they tell us how much or how many. So over here, which variables are categorical?
Name, gender, and hair.
Okay. Yeah, so what we do with name may or may not be a variable. Okay, a lot of times we'll call this an identifier, okay? It identifies the individuals, and it could just be an ID number or something, okay? But definitely gender would be categorical, and hair color, okay? So this would be categorical. So this one. And then that leaves the other two as numeric, okay? Because this tells you what if I added a third column, or not a third column, but another column over here, and we said, you know, what is your area code? And Mary says, I live in 310, and Joe says, I'm in 818, okay? That's categorical, okay? There's a number, but it doesn't tell you how much or how many. It tells you, I guess, what kind of phone area code do you have? I don't know. Okay, but it tells you what, it specifies which, so it's a categorical variable, okay? So if it doesn't give you a quantity, or tell you how much or how many, it's not going to be numeric, okay? We can further, the categorical variables, there's subtypes, okay? There's, and you don't have to worry too much, but there's even, the categorical can be further divided into nominal and ordinal. Nominal categories or ordinal. Okay, nominal is there's no natural order, and ordinal, there is a natural order to the categories. Okay. So ordinal, a good example of ordinal would be maybe t-shirt sizes. You go from small, medium, large, extra large, okay? There's a natural ordering to those categories, okay? Okay. But nominal ones, gender, okay? Should it go male, female, or should it go female, male? All right, maybe by society, we're accustomed to male, female. I don't know, okay? But there's no natural ordering for nominal categories, okay? Colors, if we're talking about vehicles and we're talking about colors of the car, okay? Is there a natural order to the car? Not really, no. I mean, we've got the rainbow, which can provide, you know, red, orange, yellow, green, blue, indigo, violet. But then, you know, what do you do with colors like black and white and silver, okay? Well, I don't know where to throw those, okay? Or something like that. So there's no natural ordering there. Even alphabetical ordering, if you think about it, it's completely arbitrary, okay? It's completely arbitrary. We're accustomed to seeing the alphabet ABC, but why? Why is it that? Okay, it's just, we're just used to it. Okay, there's nothing in nature that says the alphabet should be in this order, okay? Okay, so for numeric, how much, how many, that seems pretty normal, and this can also be further split into discrete and continuous. Discrete means only particular values are allowed. So things like number of children. People can only answer 0, 1, 2, 3, or a whole number, okay? You cannot say I have 1.8 children. So you either have 1 or you have 2. So only certain numbers are allowed. Continuous, on the other hand, you can have decimals ad infinitum, okay? So, so you can have an infinite number of decimals, okay? It is possible to have discrete things that are decimals. I don't know, maybe this is not a perfect example, but shoe sizes would be discrete, but not necessarily whole numbers. So I guess, you know, at least in America, when you get a shoe, you're either 8, 8.5, 9, 9.5, 10, something like that. So you are limited to what your shoe size is, okay? So that would be discrete. Although, you know, somebody could argue shoe size is ordinal. Some of the things, it gets a little bit blurry, okay? Just like anytime you try to categorize things, things don't always fit into nice, neat categories all the time. Continuous ones, you know, your weight would be continuous, okay? Probably most people would give answers in the whole number, or maybe to the nearest 5 pounds. But technically, if we had a very accurate scale, somebody could weigh 30.08 pounds, and somebody could weigh 130.0892 pounds or something. If we had a very accurate scale, we could get a whole bunch of decimals. At some point, we just say we don't care about fractions of pounds, but or whatever we're measuring. All right. Well, yeah, we probably don't need to spend too much here. But, okay, so let's say we wanted to take this data and we wanted to summarize it. Alright, let's say, okay, let me just add one more line here. So you have Mary, Joe, and Jesus at 6'2" and hair. Okay. So let's say we wanted to summarize this. Okay. We can summarize this with a frequency table. Okay. And we use frequency tables for categorical variables. Okay. So, for example, we can do gender, and we do frequency. And so I would write male, female, and we would say 2 males, 1 female. Okay, that's for the three lines that we have in our table. Okay, we could also have a relative frequency. And all we do is we would just turn this into a percentage, okay? So this would be 3 people total, and 100% total, and so we would say 2 divided by 3, 67%, 1 divided by 3, 33%. So that's pretty straightforward, I hope. And if we wanted to, we can make a bar chart. And we would put each category on the bottom. And we would make this one 2 units high. And this one 1 unit high. This is our bar chart. Alright, and you can imagine this being more complicated, or just a bigger table if we had a lot more entries in there. Okay, and if we did it for hair color, okay, we might have 5 or 6 bars depending on how many hair colors we would acknowledge, right? So somebody might say I've got black hair, and somebody says brown and blonde and red and gray and other colored hair or whatever. Okay. So, and then you would just have one a line there. Okay. So that is for categorical data. We've got frequency tables and relative frequency tables. Probably of greater interest would be what we do with numeric data. Okay. So for numeric data, we've got a few different tools. Okay. One is the dot plot. So with a dot plot, you first have to make a number line. Okay. And so let's say we did this for age. Okay. And with the dot plot, we would just go and every single person, we would indicate with a dot on our number line. Okay, so Mary is 24. She gets a dot there. Joseph, 26. He gets a dot there. Six dot at 19. Okay, and you could imagine that for with a larger data set. So this is, I'm just making up a fictional larger data set. Maybe the dot plot ends up looking maybe you get a dot plot that looks like that. Okay. And a dot for every single person. So this one we've got, I don't know however many people we have, but you get 1 dot per individual, or 1 dot for each subject or case. You could summarize, present the same information that the dot plot has, also with a frequency table, but this one being for numeric data. Okay. And basically here, you would put the age and the frequency, and so this is my fictional data set. So I have one person who's 18 and my frequency is 1. And some people might ask, well, should I put 19 and 0 and 20 and 0? You can, you don't have to, okay? And 21 I've got 1, and at 22 I have 4, and at 23 I have 1, 2, 3, 4, 5, 6. And you can fill out the data, the frequency table like that. Is that okay?
Mm-hmm.
All right, and then you could imagine, so this thing is called a dot plot. But for large data sets, okay, if you have a whole bunch of dots, it can be inconvenient, or it could be difficult to look at. So sometimes, we make a histogram instead. Okay, and like a dot plot, because we're dealing with a numeric variable, we have to create a number line across the bottom. Okay, so for these numeric variables, we make a number line across the bottom, and so let's say I want to do this same information here with the as a histogram. It would look something like this. And over here, I would so I could present the information using bars like this, same information. Okay, and this might work better if you've got a whole bunch of dots. So here, I don't know how many dots I have, maybe like 20 dots or so. But if you have something like 700 individuals in a table, you don't want to be putting 700 dots, okay? Or even if you had a computer do it, where it doesn't give you any difficulty in making the dot plot, it could be difficult to look at. So we might use bars instead, and we call that a histogram. Okay. This is different from a bar chart. A bar chart is what we use for categorical data. Okay. A histogram, it has bars, but it's not a bar chart. Okay. So a bar chart, that was what we had when we had male and female. This is a bar chart. Okay. With a bar chart, especially if it's a nominal category, okay, the categories can be rewritten, or the order can be changed, and I can put F over here and M over here, and it's equally valid. Okay. I could rearrange the columns or the categories, and the information is exactly the same. Over here, I cannot rearrange the categories, or I cannot rearrange the bars. Why not? Because the bars are attached to the number line, okay? And we can't say 23 comes before 20 if we wanted to, okay? The number line is fixed, okay? So we can't do that. These two equally valid. This, the order of the bars are set. So sometimes we want to, when we're talking about a numeric variable, we will talk about the shape of the distribution. Okay. So the distribution is basically just another name for how the numbers in your data set are arranged or spread out. Let's talk about the shape of a numeric distribution. So, if I make a histogram, it might look something like this, okay? And if we're too lazy to draw the individual bars, somebody might just say it looks like this. All right. So this shape we would call Well, there's two things we want to talk about when we're describing shape, okay? One, we would say this is symmetric. And the other part is we would say it's unimodal, okay? Unimodal, one peak. Okay, there's just one value that's most common, and as you move away from that value, it becomes less and less common, okay? So it could be something like the heights of women, this being maybe 5 foot 5 inches, so 65 inches being something around the most common value. And as we go further and further away from 65 inches, whether it's much taller or much shorter, women at that height are less and less common, okay? Symmetric, the idea of symmetric is, well, there's the idea of symmetry here, but in the case of numeric distributions, it means if we go a certain distance above the middle, so if I go maybe 5 inches above the middle, the frequency I encounter there is about the same frequency as if I went the same distance below the middle. Sounds kind of awful, but well, basically we're saying, okay, let's say for women 65 inches is the most common height, something around there is true. Okay, so if I go 5 inches above that most common height to 5 foot 10, 70 inches, okay, maybe I'll have a certain number of women about that tall. What the symmetric part says is that if I went that same distance below the middle, so if I went 5 inches below the middle down to 60 inches, I would have about the same number there as I do up here. Okay, that's what we have for symmetry. On the other hand, we can talk about other shapes. So we have skew. Okay. So this thing we would call is skew right. And over here I would have, this would be skew left. Okay, both are unimodal, both have one peak, most common value. So these are both unimodal. But the shape here is skew right and skew left. So the idea over here is that maybe middle is somewhere around here. And with skew right, what we're saying is that, you know, if I went this far out here, okay, I've got some people who are way above the middle. And if I went the same distance down here, I don't have anybody that distance down below the middle.
Is middle considered the same thing as average?
Yeah, well, I'll explain on this concept of middle. The average, we'll get to that in a moment.
Okay.
Yes. So Yeah, we can talk about average, but we've got a few definitions for average, median and mean. So we'll get onto that. But when we're talking about shape, what it means is that if I want a certain distance above the middle, I have some people, maybe not a lot, but some people out here, and if I want that distance below the middle, I don't have anyone. So, yes?
Why is it called the right when it looks like the hump is on the left?
Yeah, so it's where the tail goes, okay? So if you're having trouble, just imagine if I were to use this as a weapon, okay, if I were to cut this out of the board and use it as a weapon, or maybe not as a weapon, but if I were going to cook shish kebab, pieces of meat on it, which side would I use to skewer the meat? Okay, here I would use the left side, and over here I would use the right side, right? I would put my pieces of meat over here. Yeah, so it's where the tail goes, okay? And so this may be something like weight, human weight is skewed right. Okay, so, I don't know, average male in the United States, about 170, 180 pounds. Okay, so let's say 180 pounds, average male. Okay, some men weigh 360 pounds, okay? Not a lot, but there are men who weigh about that much. Okay, so we've got some. So 360 pounds is 180 pounds above average. All right. If I go 180 pounds below average, that takes me to 0 pounds. Okay. Are there any adult men in the United States that weigh 0 pounds? No, it's impossible. Okay. Nobody can exist and weigh 0 pounds. So that is something that's skewed right. Okay, you have some people who are way out here, and if you want that same distance over here, nobody exists. Okay. Skew left, it's just the opposite. This could be something like test scores. Okay, maybe average for an exam is like 80% or something. Okay, and you'll have people who score maybe like 30% on an exam, right? Way below average. Not a lot, but some people will score really low on an exam. So 30% would be like 50 points below average. If you go 50 points above average, it takes you to 130%. Okay? Now, assuming this is just a regular old exam where 100% is the maximum, you won't have anybody that much higher than the average. Okay, so you got skewed right and skewed left. Is that okay? Alright, so we talk about symmetric, skew right, skew left. And then we have so anything with one peak we call unimodal. And then if it's got 2 peaks, bimodal, and then if it's got more than 2, we'll say multimodal. So 1, 2, or many. I mean, you could say trimodal, quadmodal, although it's not very common. You don't really say. Usually unimodal and bimodal. Multimodal, okay. So what might something be bimodal? Yeah.
If you're examining a phenomenon over time, like you might see 2 peaks if something is, say, repeating itself.
Okay. So that might be true, but I'm having a tough time because over these things, what kind of data are we dealing with here? Numeric data, right?
Mm-hmm.
So with numeric data, we're just kind of lumping them all together, okay? We're not going to really learn time series in this class. So we're just lumping them all together. So we're just taking all the measurements all at once, and so there might be peaks, but I don't want to say something about anything involving time yet. So yes.
Weather?
Huh?
Weather?
What about, okay, like
The temperature?
So the temperature. So I would say temperature is probably unimodal. Okay.
But throughout the day, it goes up and it comes down.
It does go up and it does come down, but overall, if you took measurements throughout the day on the hour, you probably won't see two peaks. You'll probably see one peak overall. The average temperature in some parts of the day was higher, and other parts of the day, times of the day was lower. Because remember, there's no time association here. We're just throwing all the numbers together. Yes.
The number of people married in different age groups.
The number of people married in different
Like maybe
age
in
groups.
their 20s, there's like, a certain amount.
Okay, I
maybe 30.
think that's a categorical variable, okay? Married or not married would be categorical. So, okay. Alright, we'll take a couple, I'll just give you an answer later, but yes.
What about something like life expectancy, where like people are gonna, there's a good chance that if you make it over a certain hump, you're gonna, like, it's gonna be staggered, so it's not just gonna be one average age, it's gonna be a couple different ones,
Oh, so, like if we took everybody in this classroom and we said everybody's life expectancy right now,
Yeah, no, yeah, everyone's at like the average life
that's
expectancy. is not gonna
probably
happen
going to
anymore.
be less skewed, I would imagine. I would imagine most people's life expectancy would be, or maybe it's right skewed. Most people's life expectancy would be around a certain number, and I wouldn't expect, I don't expect, basically, I'm not expecting a certain age where life expectancy doesn't exist or something, so. Okay, well, last one, I'll just give you an example, yes.
What about, if you had average height in the population, including males and females?
Okay, that actually could be bimodal, and it depends on how different men are from women. So this has been long debated, and there's no final resolution. And if it is bimodal for height, it might look something like this, okay? Where, yes, men on average are taller than women, okay? And you got some men who are taller than other men, and some men who are shorter than other men, and you got some, so this might be the average height for women, the average height for men, and some women are taller than other women and others are shorter. So it might be like this. Others might say it's just kinda like this. Alright, so and this is debatable, but that's actually a very good example. Height across the population, where we see Tita, and then you got excited about something.
Traffic over time.
Traffic over.
Like there's rush hour and then rush hour after.
Uh,
And then the variable would be time.
Okay, well, how are we measuring traffic?
How heavy it is. How many cars are on
Okay,
the
so
freeway?
let's say, okay, cars per square meter on the 405, and but not at different times of day, because remember, this is just a single numeric variable, right? So maybe throughout the day, I can say, 6 a.m., 7 a.m., 10, 8, 9, 10, 11, 12, 13, 14, all the way throughout the clock, and yeah, these are high numbers at 8 in the morning and high numbers, but then when I just throw them all together, remember, because this is just a single, I'm not associating the time here, I'm just taking the one numeric variable and I'm making a histogram. I think what we might see is just certain, just one number, I don't know. I guess I have a feeling it'll be kind of left skewed-ish. I don't know. Maybe, I have to think about that a little bit more. A lot of things biologically relating to the differences between the sexes will be bimodal. So one that will be a lot more stark will be testosterone levels, okay? So everybody has some testosterone in their body unless something is wrong. And men will have, there will be kind of an average testosterone level in men. Some men will have more testosterone than others, and some men will have less testosterone than others, okay? And then there will be an average testosterone level for women, okay, which is lower than the male level, and some women will have more testosterone than other women, and other women will have less testosterone than the average woman, okay? and you'll have kind of this middle zone where you don't have very many women with super high testosterone levels or very many men with dramatically lower testosterone levels. You don't have very much in this middle region, okay? So testosterone levels would be something bimodal, okay? Similar with vocal pitch, okay? Your vocal pitch also, you'll have two distinct things, and then when you meet someone who's somewhere in the middle, there's something a little bit, I don't know, striking, right? So average women vocal pitch will be much higher than average male, and then so Margaret Thatcher, she worked with a vocal coach to purposely bring her vocal pitch down because that would, I guess, cause people to respect her more subconsciously somehow. So things like that happen. Okay, so vocal pitch, testosterone levels, those are very clearly bimodal things. Other things show up as bimodal as well. But yeah, I know a lot of you have these ideas, but you have to, with this, things throughout time, yes, might indicate ups and downs, but we are treating these as just one variable at a time, is kind of how things will go. Okay. Shapes and distributions. All right. So let me see how much time we have. All right. So I got about half an hour. All right. So let me talk about measures of center. Alright, we have the mean, and we have the median. Alright? The mean is, you add up all the numbers and you divide by how many numbers you have. Add up the numbers and divide by how many you have. So for the mean, we use the symbol y bar. Okay, sometimes we use x bar. Okay, y bar or x bar, and to say add up all the numbers, we use this symbol, which means sum. Sum of all of the y's, divide by n, the number of numbers you have. Yes, question.
Just going back to the multimodal. What did you have an example for that at all?
I don't know, average number of years in school, number of years in education, okay? So you'll have a lot of people, 12 years of education, graduating from high school. Then you'll have a lot of people with 16 years of education, they finished a 4-year degree. And then you'll have maybe 18 people who went on to get their master's degree. You don't have as many people getting something like 17 years of education or 19 years of education or things like that. So you'll see these peaks, and if you asked, how many years of education have you had? Okay, well this class is going to be different because a lot of you are currently in school right now, so you'll be the in-between ones. But if you just ask the overall population of adults, they will say, I graduated high school, so I had 12 years of education, things like that. So. Okay, add up the numbers, divide by how many you have, that's the mean, okay? The median is, this is the middle number. Okay, half of the points are above the median. And half are below the median. You have, if you have a set of numbers, a large set of numbers, so, or just in any set of numbers.
Thank you.
Okay, the median is the n plus 1 over 2 ranked number. What does that mean? Okay, Well, it means, okay, if you rearrange all of the numbers in rank, okay, so rank all the numbers, or rearrange them from largest to smallest or smallest to largest, so whatever you have. Let me just find some numbers that we can do an example with. Sorry. Okay. Okay, so let's say these are some numbers we get. Alright. So I've arranged them from smallest to largest. So how many numbers do I have? I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. Okay, so here my n is equal to 14. Okay, so it's the number in the n plus 1 over 2 rank. Okay, so n plus 1 over 2 would be 14 plus 1 over 2. I get 7.5. Okay, so if I rank these from smallest to largest, this is my first place number, first, second, third, fourth, fifth, sixth, seventh, and eighth number, okay, and so on and so forth. So my 7th rank number is 20, and my 8th ranking number is 22. So the number, my median is the number in the 7.5 position. So it's the number between 7 and 8. So at this point, I would just take halfway in between the 7th and 8th place number. So I would do 20 plus 22 divided by 2. So my median is, I'm sorry, 21, not 21 and a half, it's just 21. So that's my median there. Is that okay?
Mm-hmm.
And then indeed, 7 numbers are smaller than 21, 7 numbers are larger than 21. We also have numbers called quartiles. Okay. So the median splits our basically our list into half, and the quartiles will split the list into basically quarters. Okay, so we've got Q1, Q2, and Q3. All right, and I guess technically there's also Q4. Okay. Q1 means 1/4, or 25% of the data. 1/4 of the data is smaller than Q1, okay? Q2, 2/4 of the data, or 50%, is smaller than Q2. Q3, how much is going to be smaller than Q3? 75% is smaller than Q3, and Q4 would be 100% is smaller than Q4. Alright? So Q4, in other words, Q4 is the largest number in your data set. So Q4, we just call that the maximum. And Q2, what's the other name for Q2? The median, right? Half of the numbers are smaller than the median, half of the numbers are smaller than Q2. So Q2 is the median, indeed. So we don't really talk about Q2 and Q4 very often, okay? In terms of quartiles. So we'll have Q1 and Q3. So how would I find Q1 to get the number we're 25% smaller than Q1? Okay. Well, first,
Wait, wouldn't Q2 be the mean, not the median?
not the median, okay? The median is the middle number, half are above and half are below the median.
Okay, sorry, I thought we were talking about, oh yeah, okay, I guess that makes
Okay.
sense, sorry.
Yeah, the mean we find by adding up the numbers and dividing by how many we have, okay? That's the mean. The mean can also be thought of as the balance point in our data, the balancing point in our data. That's mentioned in our textbook. The mean is the balancing point. But anyway, we got Q1 and Q3. And to get Q1, well, first we would find the median, and we split our list in half, and now I just ignore half of the list, and so I've got 7 numbers over here, and I find the median of these 7 numbers. That's going to give me Q1, right? So I'm just taking the list in half, and then I'm splitting it in half again. So I got 7 numbers over here. So what's the middle number of these 7?
15.
Yeah, it's this one right here, okay? So this is Q1, okay? And what's Q3? 30. Okay. That's Q3. Let me change this last number from 48 to 58. Sorry. Illustrate. So is that okay, finding the quartiles and the median? The median and the quartiles?
Q4 would be 58?
Yeah, Q4 would just be the maximum,
Okay.
58. Okay. Yeah, so we also have the maximum and the minimum, which are just the largest and smallest values. Alright, there is a graphical summary that we can use called a box plot. Alright? And just like every other numeric variable, every other tool to display a numeric variable, we have a number line going across the bottom here, okay? So maybe, and so with a box plot, you draw a box. You have a box, and the boundaries of the box are Q1 and Q3. So I draw a box, okay, and the edges of the box are Q1 and Q3. I draw a line down the middle of the box, or in between the box, at the median, okay? So my median was 21. So I draw a line right here, and this is my median. So that forms our box, okay? So box plots are kind of like very quick summaries of data, okay? Very quick numeric summaries here. We got Q1, the median, and Q3, all right? And then I extend the lines from the box, these are known as whiskers, that go to the smallest and largest points within the fences, okay? The book calls this a modified box plot, but everywhere else, this is just known as a box plot, okay? So we have these invisible boundaries called fences. Fences kind of distinguish what between, I guess, the regular data and what could be considered unusual, okay? So we've got fences, separate quote, unusual from usual, okay? And I should say potentially unusual, because not everything is necessarily unusual. Alright, and the fences go, basically, you take the width of the box, you multiply it by 1.5, and you go that far above the box and that far below the box, okay? The width of the box, which is Q3 minus Q1, has a name, and that's called the IQR, the interquartile range. So the IQR is the inner quartile range, and that is Q3 minus Q1, the width of the box. What percentage is within the box? What percentage of the data is within the box? 50%, 50%, right? Because Q3 is the 75th percentile, and Q1 is the 25th percentile. 25% smaller than 1, and 75 is smaller than Q3, so that 50% is within the box. So you have the upper fence at Q3 plus 1.5 times the IQR, and then the lower fence is Q1 minus 1.5 times the IQR. Okay, so where is my upper fence and lower fence?
30 is your upper.
Yeah, so 30 is Q3, so and my IQR in this case is 15, right? So if I do Q3 minus Q1, I get 15 as my IQR. And then so my upper fence is equal to Q3 plus 1.5 times the IQR. So I get 30 plus 1.5 times 15. So I think that's 22.5 plus 30. So my upper fence is 52.5. So I draw an imaginary line at 52.5. Okay, and then I do the same thing on this side. So I get an imaginary, my lower fence, if I figure it out, is at negative 7.5. Okay. Upper fence at 52.5, and lower fence I would do Q1 15 minus 1.5 times my IQR. If you figure it out, you get negative 7.5. So with this data set, I draw lines or whiskers that extend to the largest and smallest point within the fences. So what's the smallest point that I have here? 8. Okay, is that within the fence? Yes. So I draw a line that goes down to 8. What is the largest point that I have over here? It's 58. That's beyond the fence, so I don't draw a line there. The largest point that I have within the fence is 35. Okay, so I draw a line that goes up to 35. What do I do with 58? Anything outside of the fences I represent with little circles or stars. And that indicates I do have a data point there, but it is beyond what I would consider usual. So this point, compared to the other data points that I've collected, this is unusual. Okay, we might call it an outlier.
So does that mean technically you're just throwing that out?
I'm not throwing it out. I'm saying it's there, but it's unusual. It's unusual, okay? So for example, if we said, go around, I don't know, we're not gonna do this, but we say, okay, everybody go around and tell us, you know, how much money you have, okay? And everybody says, oh, I've got this much and this much and this much money, okay? And then let's say Bill Gates walks into the room, okay? And he's got whatever, something $1 billion. Alright, if we drew a box plot with everyone's money, okay? Well, probably all the money you have is probably, you know, some number that is not anywhere close to Bill Gates's assets, okay? And so, so you would have a box plot that includes everybody in this classroom, basically, and then Bill Gates would show up, and we're not ignoring him, but he just shows up as a dot all by himself, and that indicates he is unusual compared to everyone else. Yes?
Sorry, so you got the whiskers by taking
So the whiskers, maybe I'll write this somewhere on the board. Whiskers go to the largest and smallest points in the data set that are still within the fences, okay? Whiskers go to the largest and smallest data points within the fences. All right. We are running out of time, and there's a concept that I didn't really get to cover. So, and that is the standard deviation, and that's an important concept. And so we'll talk about that. I've created a video already about the standard deviation, okay, that I want you guys to watch as part of your homework this week. All right. So, the standard deviation is a measure of dispersion or spread. Okay. The IQR is another measure of dispersion. It tells us when we have a set of numbers, the IQR gives us an idea of how spread out those numbers are. The IQR tells us where the lower quarter is and where the upper quarter is, and it tells us about how different is this lower quarter from the upper quarter. The standard deviation gives us an idea of how spread out our numbers are, but it uses a different concept, okay? It's kind of the average of distance from the mean, okay? So we say if the mean is located here, about how far are the points away from the mean, okay? Some points are very close to the mean, some points are much larger than the mean or far away, okay? And the standard deviation is kind of like, what is the average distance from the mean? But it's not really the distance because we square that distance and then we take the square root later. So it's like, if I squared this distance, how far is it away from the mean? It feels a little bit odd at first, but we're going to be using it quite a lot, and it gives us an idea of how different, how similar things are, or how different things are. So just hang on a second. So one example is if we went around the classroom and we said, you know, how much do you weigh? Okay, and if we all shared, we would see probably a wide range of weights. Some people weigh more, some people weigh less. Okay, the standard deviation there would be quite different. Okay, now if we went to a car dealership, okay, and we said, okay, show me all of the one particular model car. Okay, we say, show me all of the Honda Civics you have. Okay, and we weighed every single Honda Civic. Okay, they're probably going to weigh fairly similar to each other. Some might weigh a little bit more than others, okay? But we would not expect a huge range of weights between the different Honda Civics, especially if we're all looking at one model, okay? So we would expect kind of a smaller standard deviation there, and maybe among different people we'd see a large standard deviation. So even though the cars weigh more, okay, the standard deviation just tells us about how different are the different weights from each other, okay? And you'll see a little video just explaining, breaking down the process and calculating that out. Okay, so we'll pause there, and we'll see you guys next week.